Somewhere on the coast of Normandy, inside a building longer than 3 football fields laid end to end, a single machine part is being born that will be longer than the wing of a Boeing 747, and it is made almost entirely of glass, wood, and glue. It sounds impossible. A single piece of equipment, over 100 meters from root to tip, engineered to flex like a fishing rod, twist like a diver's body in midair, survive 25 years of hurricane-force winds without ever being allowed to fail, because if it fails hundreds of feet above the ocean, attached to a machine worth tens of millions of dollars. And yet this object is not built, is grown layer by layer inside a mold. The way a shipbuilder once built wooden hulls plank by plank, except every plank here is thinner than a sheet of paper, and the entire structure will be injected with liquid resin and left to cure into something as strong as steel, lighter than aluminum. This is the story of how a wind turbine blade is made. And it begins with a question that almost nobody asks when they see turbines spinning lazily on a distant hillside. How do you manufacture something this big, this precise, and this strong at a rate of dozens per week, without a single visible seam, weld, or bolt along its entire outer skin? The answer will take you through Ecuadorian rainforests, French shipping ports, robotic arms that never sleep, and a quiet engineering revolution that most people have never noticed is reshaping the modern factory floor. To understand why this process exists at all, you have to go back to a much smaller, much humbler machine. The earliest wind turbines of the 1970s and 1980s carried blades scarcely longer than a school bus. It's hand-laid by small teams working, with fiberglass mats and resin brushes, more craft than industry. A Danish furniture company called Lunderskov Møbelfabrik, founded in 1942, build wooden furniture, found itself pulled into this strange new industry almost by accident, discovering that the same skills used to shape curved wooden furniture parts translated surprisingly well into shaping the aerodynamic curves of a rotor blade. That company would eventually become LM Wind Power, and by the time it partnered with General Electric decades later, the blades it built had grown from under 10 meters to over 100. A tenfold increase in length that represents something far more dramatic in terms of the physics involved. Because the swept area of a rotor, and therefore the energy it can capture from the wind, scales with the square of the blade length. Double the blade, and you don't just double the power. You roughly quadruple it. That single fact is the economic engine driving every decision. But bigger comes with a brutal engineering penalty. A blade that has grown tenfold in length has grown roughly 1,000-fold in the potential structural loads acting on it, because bending forces increase disproportionately with length. An engineer at a blade factory once described the challenge simply: you are building something the size of an airplane wing, except it has to survive spinning in place for 2.5 decades, enduring millions of stress cycles, in salt air, in freezing rain, in tropical humidity, without the luxury of ever landing for a full inspection. Airplane wings get regular maintenance in climate-controlled hangars. A wind turbine blade, once installed 100 meters above the ground or bolted to a foundation rising from the seabed, is expected to simply endure. That single constraint is why the manufacturing process you're about to witness has become one of the most demanding composite fabrication challenges in modern industry, more exacting in some respects than shipbuilding, and increasingly comparable in precision to aerospace manufacturing itself. The story begins, strangely enough, not with steel or carbon fiber, but with a lightweight tropical hardwood. For decades, the vast majority of the world's wind turbine blade cores were built using balsa wood. And nearly all of that balsa, somewhere between 2/3 and 90%, of the entire global supply came from a single country, Ecuador. Balsa has a peculiar cellular structure, a natural honeycomb of microscopic air pockets that make it remarkably light while still providing outstanding compressive strength, which is exactly what's needed to sandwich between layers of fiberglass and prevent a thin composite skin from buckling under load. For years, this worked beautifully. Strange and little-known dependency where a global renewable energy boom rested, quite literally, on a South American tree farm. Then, starting around 2020, demand exploded so quickly that legitimate plantation supply couldn't keep pace. And reports emerged of illegal logging pushing into the Amazon itself, of social conflict in indigenous communities, of a phenomenon local suppliers nicknamed balsa fever. It became one of the wind industry's quietest controversies, a technology built to fight climate change, was, in isolated cases, contributing to deforestation pressure in one of the planet's most important ecosystems. The industry's response reveals something important about how modern manufacturing solves problems under pressure. Engineers didn't panic and they didn't ignore the crisis. They engineered their way out of it, accelerating the shift toward PET foam, a lightweight polymer core material. Increasingly manufactured from recycled plastic bottles, it could match much of balsa's performance without depending on a single vulnerable ecosystem. By the middle of this decade, PET foam had gone from a niche alternative to one of the dominant core materials in blade manufacturing. Alongside PVC foam, with balsa now used more selectively in regions of the blade where its specific mechanical properties still outperform synthetic alternatives. It is a small case study in a much larger truth about factories at this scale. Every material choice ripples outward into global supply chains, labor markets, and ecosystems, thousands of miles from the factory floor. And every material substitution is itself a small act of engineering problem-solving under real-world pressure. Walk into one of these factories today, whether it's a coastal facility in Denmark, a sprawling complex in Castellon, Spain, or the newest and largest of them all, along the English Channel in Cherbourg, France. The first thing that strikes you is the scale of empty, open space. These buildings are less like a traditional assembly line and more like enormous aircraft hangars, because the object being built simply will not fit through a normal factory door once it's finished. At the heart of each hall sits a mold, and this is where the real engineering story begins. A blade mold is not a single reusable die stamping out identical parts the way a car door panel gets stamped in seconds. It is a massive, custom-built, temperature-controlled tool, often over 60 meters long for onshore blades and well over 100 meters for the newest offshore giants. Machined to unbelievably tight tolerances because every imperfection in that mold surface becomes a permanent imperfection in the aerodynamic skin of the finished blade. Two of these molds exist for every blade, one shaped like the pressure side, one like the suction side. Mirror images that will eventually be joined together like a shell closing around its contents. The construction of a blade begins with what workers call the layup. And it is here that the process starts to look less like heavy industry and more like an extraordinarily delicate form of textile work performed at a monumental scale. Technicians, sometimes assisted by automated fiber placement systems and increasingly by robotic arms, begin laying sheet after sheet of dry fiberglass fabric into the mold, following a design that has already been simulated, stress-tested, and optimized by structural engineers using software that models decades of wind loading in advance. In the highest stress regions of the blade, particularly along what's called the spar cap, the structural spine that runs the length of the blade, much like the central beam of a bridge, engineers reach for something stronger and lighter than glass fiber: carbon fiber. Carbon fiber costs dramatically more than fiberglass, so it's used surgically, concentrated exactly where the bending loads are most severe. An elegant compromise between performance and cost that appears again and again throughout the blade's design. Some manufacturers, notably Siemens Gamesa, developed proprietary methods of preforming these carbon fiber spar caps using a process called pultrusion, essentially pulling continuous fibers through a heated die to create rigid, pre-cured structural strips that are then set directly into the mold, like the keel of a ship, dramatically improving both the consistency and the speed of production compared to hand-laying carbon fiber sheet by sheet. Between the layers of fiber skin, workers install the core material, whether balsa, PET foam, or a combination of both, depending on the specific structural zone, arranged in a pattern that engineers call a sandwich structure. Exactly the way a slice of foam or honeycomb between two rigid skins in an airplane fuselage panel gives enormous stiffness for very little added weight. Every sheet, every core panel, every reinforcing strip is placed according to a design that can specify literally hundreds of distinct material layers, changing thickness and orientation along the blade's length. Thicker and more reinforced near the root, where the entire enormous bending moment of the blade must be transferred safely into the turbine's rotating hub, and progressively thinner and more aerodynamically refined toward the tip, where the blade experiences its highest velocity and must remain light enough not to overload the entire rotating assembly. This is where the paradox of large-scale manufacturing meets an almost artisanal level of care. Robots and automated systems are increasingly involved in cutting fabric to walking the length of the mold, smoothing wrinkles from fabric that will soon be invisible forever. Aware that a fold or an air pocket introduced now could become a structural weak point that engineers might spend years searching for after the blade has already spun through 1,000 storms. Once the dry fiber layup is complete, the blade shell enters one of the most crucial and least visible stages of the entire process. Resin infusion, a giant vacuum bag. Essentially, an enormous airtight plastic film is sealed over the entire mold. Pumps draw out every trace of air from within the layered fabric, creating a vacuum that will pull liquid resin through the dry fibers the moment it is introduced. This technique, called vacuum-assisted resin transfer molding, replaced older and messier hand-layup resin methods because it dramatically reduces the risk of air bubbles, uneven saturation, or the kind of microscopic voids that can quietly undermine composite structures. Strength for years before finally causing a fatigue crack. Engineers monitor the resin's flow in real time, watching pressure sensors and flow fronts as carefully as a surgeon might watch vital signs. Because a resin front that stalls or races ahead unevenly can leave a dry, saturated patch of fiber buried invisibly inside the finished blade, a hidden flaw that might not reveal itself until years later. Spinning silently above a wind farm. Once the resin has fully saturated the fiber layup, it must cure, typically inside a heated mold, sometimes assisted by embedded heating elements or a climate-controlled hull. Transforming from a liquid into a rigid thermoset polymer through a chemical reaction that, once triggered, cannot be undone. There is no reworking a blade shell after this stage. Whatever imperfections exist are now permanent, sealed inside layers of glass and carbon that will never be opened again. Which is precisely why every earlier step, every sheet of fabric, every vacuum seal, every resin sensor reading matters so enormously. With both shell halves cured and removed from their molds, the blade enters its most dramatic and dangerous-looking phase, assembly. Before the two shells can be joined, workers install the internal shear webs, vertical structural panels that run down the interior length of the blade like the ribs of a canoe, transferring loads between the pressure and suction side shells and preventing the entire structure from twisting or collapsing under aerodynamic force. Adhesive, a specially formulated structural epoxy, is applied in careful, measured beads along every bonding surface, and then, in a moment that never fails to look almost absurdly delicate given the scale involved, one shell is lifted and rotated by overhead cranes and lowered with millimeter precision onto the other, closing the blade like a clamshell around its internal skeleton. Once closed, the entire structure is clamped and left to cure again, the adhesive bond lines becoming in effect. Invisible welds holding together what is now unmistakably a single object rather than two halves. It is worth pausing here on something easy to overlook, this bonding process. This gluing together of two enormous curved composite shells represents one of the most critical failure points engineers watch for over a blade's lifetime. And improving the reliability of this single step, the adhesive bond line running the entire length of the blade, has consumed more engineering research hours in the wind industry than almost any other single manufacturing challenge. Inside the layup hull, the atmosphere itself becomes part of the manufacturing process. Humidity, temperature, and even dust particles in the air are tightly controlled, because a stray fiber of contamination or a spike in ambient moisture can interfere with resin chemistry days later.
How workers
move through the space in a kind of choreographed rhythm, some walking the mold's edge on suspended platforms that travel the entire length of the blade, others operating overhead gantries that lower massive rolls of fabric into position with a precision that would have been unthinkable for the small hand-built blades of the raw 1980s. It's a strange blend of eras happening simultaneously on the same factory floor. Robotic ply-cutting machines guided by computer-aided design files sit meters away, from technicians pressing wrinkles out of fabric with nothing more than their gloved hands and years of trained instinct, because even now, with automation advancing every year, there remain certain judgment calls, whether a wrinkle is severe enough to require rework, Whether a resin flow front looks slightly off, that experienced workers can catch faster than any sensor. Factory managers describe this tension candidly. Automation increases consistency and throughput, but the industry hasn't yet reached, and may never fully reach, a point where human judgment becomes unnecessary in a process this structurally unforgiving. Every blade that leaves one of these factories carries, quite literally, the fingerprints of both a machine's precision and a human's watchfulness. Underlying mathematics that has pushed blade length for 50 straight years. More swept area means more captured energy, which means lower cost per unit of electricity delivered to the grid, which means renewable power that can compete on price alone rather than requiring subsidy. Every additional meter of blade is, in a very real sense, an act of economic engineering as much as structural engineering. But length alone doesn't tell the whole story of where this industry is heading, because the factory itself is transforming almost as dramatically as the blades coming out of it. Automation is steadily creeping into stages of production that were, until recently, almost entirely manual. Automated fiber placement machines now handle some of the most repetitive and precision-critical layup tasks, laying material with a consistency that reduces the human variability that has traditionally been one of composite manufacturing's most persistent quality challenges. Sensors embedded directly into molds now track resin flow, its temperature, and vacuum integrity throughout the infusion and curing process.